Hello, and thank you for joining us. Today, we're going to talk about everything that you, as a printer, need to know about viscosity. We'll start with a basic definition of viscosity, then discuss why it matters to you. Next, we'll look at various ways of measuring and controlling viscosity with a specific focus on the strengths and weaknesses of each method to help you decide which method is best for you. We'll also cover the intractable relationship between temperature and viscosity, and just as we did with viscosity, we'll look at the various ways of controlling temperature, identifying the strengths and weaknesses of each method, again to help you decide what's best for your printing operation. Finally, we'll look at the benefits controlling the viscosity variable can bring, and then provide you with some resources to point you in the right direction. So let's get started. So what is viscosity anyway? Well, if we start with Google, and who doesn't, we actually get two interesting views. The first is how we all understand it, the state of being thick, sticky, and semi-fluid in consistency. Then it leads into the more scientific definition with due to internal friction. This is how Sir Isaac Newton defined it in his famous book, The Principia, first published in 1687. Paraphrasing, viscosity is a quantity expressing the magnitude of internal friction as measured by the force per unit area resisting a flow in which parallel layers unit distance apart have unit speed relative to one another. A bit confusing? Perhaps. Let's go back to how we understand it. A somewhat simpler explanation is the property of resistance to flow in a fluid or semi-fluid. Water is the universal definition of a fluid. But what is a semi-fluid? Honey is a great example. Think of honey when you put it in the refrigerator. It gets thick, very thick, in fact almost solid, and sticky too. But take that same honey and place it in the sun on a hot day, and the change is dramatic. It thins out significantly, and you can pour it, almost like water. This change in how it flows represents its change in viscosity. In this case, the cause is the change in temperature. But we'll talk more about that later. So why should I care about viscosity? First, because of color changes or variations during a press run. Since color is dependent on viscosity, measuring and maintaining the ink viscosity throughout the press run is crucial to ensuring consistent color. Manually controlling or spot checking during the run does not allow for true viscosity and color control. Next, ink's not drying or drying too quickly. When manually measuring and controlling ink viscosity, there is always the possibility that the ink to solvent ratio may not be correct for the volume of ink being applied. This can result in ink drying either too quickly or not quickly enough. Variation in ink drying time can lead to a variety of print-related issues, including inconsistent color, bleeding, smearing, and flaking. Each of these may cost valuable time, labor, and lost income due to rejects. Then there are cost issues like excessive ink usage during a press run. With manual viscosity monitoring, the ink can have large swings in viscosity due to the many other functions the operator is responsible for. This results in only occasionally checking and adjusting the ink. As solvent evaporates, ink viscosity rises and more ink is applied to the substrate. And excessive solvent, amine, or extender usage during a press run. With manual control in place, the possibility of adding too much solvent or amine when dosing is increased. This haphazard approach will certainly affect the ink color. Additionally, since these additives are poured in, not metered in, there is limited control on the amount used. And then, there are quality issues you normally might not associate with viscosity, like adhesion or flaking issues. When manually maintaining ink viscosity, there is a risk of adding too much or too little solvent to bring the viscosity back into spec. Further, if different solvent blends are used for different inks, the chance for adding the wrong solvent exists, which can result in contaminating the ink and causing additional problems. Dirty print or ink smearing. If the ink viscosity is not adequately maintained throughout a press run, the ink viscosity rises and falls due to solvent evaporation and replacement. The ink may adhere to or build up on the plate, impression roller, or substrate outside of the impression area. This may cause dirty print or smearing in non-image areas. This can result in job rejections due to print-related issues. For most companies, brand is one of their most important marketing tools. Anything associated with it comes under greater scrutiny, and expectations for a higher quality print job become the norm. If the color associated with the brand is not correct, or if there are any print-related imperfections, there's a higher chance for a job to be rejected. Often, these rejections or customer returns can be traced back to inconsistent ink viscosity. And let's not forget about operational issues. For instance, Analox roller cells plug up. Improperly maintained or inadequately mixed inks can result in ink solids trapped in the Analox cell, creating print imperfections. This causes print-related problems such as deformed dots, dirty print, or other issues. This is often due to improperly maintained viscosity. Additionally, ink viscosity directly affects the transfer of ink from the Analox roll to the plate. This changes the volume of ink applied to the substrate and therefore the color and intensity of the image. This is the reason that many printers use different Analox rolls at different times of the day or year. Excessive cleanup time due to ink-related issues. If you have housekeeping issues around the ink pail and throughout the press, you may have a viscosity-related problem. Ink management, including viscosity control and mixing, can aid in ensuring fewer issues with ink slinging. Commonly, this slinging is the result of either thin ink or buildup due to out-of-range viscosity. Press stoppage during a run to address cleaning-related issues. Proper ink management can reduce the number of times it is necessary to stop a press during a run to clean plates, rolls, or other press areas due to ink buildup or slinging. So now that we understand that there are a host of common issues associated with improperly managed ink viscosity, how can I control it? In order to control something, you have to be able to measure it, and there are several ways to measure viscosity out there. The most common are the Efflux or Zahn cup, the falling piston or ball, vibrational, torsional, rotating plate or cone, and the list goes on. Each has its pros and cons, and each is better for some applications than others. The key to success is starting with the optimal measurement process and from there identifying the optimal control strategy. So let's look at the most common ones used for printing process control in a little greater detail. We start with the common Efflux or Zahn cup. Essentially, an Efflux cup is a container with a hole at the bottom. The cup is lowered into the ink to be measured, then lifted out. When the hole is above the surface of the ink reservoir, a stopwatch is started, and the time it takes a fixed quantity to flow out of the hole can be measured. Obviously, this is a totally manual process and is therefore performed periodically, not continuously. The accuracy of the ink control is a function of the frequency of measurement, the care taken by the press operator when he performs the measurement, and the way he chooses to react to the value he gets. Next is the falling piston viscometer. This is the oldest and most proven of the inline measuring strategies out there. The piston is raised by a pneumatic lifting mechanism, drawing the ink being measured down through the clearance gap between the piston and the wall of the cylinder into the space which is formed below the piston as it is raised. The piston assembly is then typically held up for a few seconds, allowing the system to equalize. Then it is released and allowed to fall. Pulled by gravity, the sample is expelled out through the same path by which it entered. This creates a shearing effect on the measured liquid. This makes the viscometer particularly sensitive and exceptionally good for measuring certain thixotropic liquids. The time of fall is a measure of viscosity. With the clearance between the piston and inside of the cylinder forming the measuring orifice, the viscosity controller measures the time of fall in seconds and then converts it to a common viscosity value and displays the result. This can be converted to any common value like centipoise, centistokes, Zahn cup seconds, Din cup seconds, etc. The vibrational or tuning fork viscometer measures the damping of an oscillating resonator. Generally, this oscillates transversely as a tuning fork. The higher the viscosity, the larger the damping imposed on the resonator. This damping may be measured by one of a couple of methods. First, measuring the power input necessary to keep the oscillator vibrating at a constant amplitude. The higher the viscosity, the more power is needed to maintain the amplitude of oscillation. Or measuring the decay time of the oscillation once the excitation is switched off. The higher the viscosity, the faster the signal decays. So which viscosity measurement is the most effective? Well, that depends on your situation. To make that determination, let's review the most common methods, discuss their strengths and their weaknesses, then summarize each. We start with the Efflux cup. Its strengths are that it is inexpensive. The Efflux cup is by far the least expensive of these options. It's quick. Getting a reading takes a very short period of time. Zahn cup times are generally measured in seconds. It's easy. It's simple to use and easy to train someone to use. And it's the benchmark. Cup seconds is the common language in the printing industry, and many others as well. It is often the go-to measurement when discussing viscosity and viscosity issues. Its weaknesses include people. While easy to use and easy to train others, it relies on the human element. We have seen as much as a 30% variance in viscosity reported by operators using Zahn cups. Simply stated, it leaves an awful lot open to interpretation, attention, and personal preference. Then there's time. If you're taking cup measurements every 15 to 20 minutes, you are considered to be staying on top of it. The reality is, much can change in a printing process in that time, leaving you exposed to quality defects. Temperature. According to Digitis Industry in 2005, a temperature increase of just 5.5 degrees C can reduce the viscosity of a printing ink by 50% or more. By taking ink out of the process and subjecting it to temperature change due to ambient conditions or the temperature of the cup itself, you eliminate the possibility of getting a true process reading. Then there's shear. Most common process fluids, inks included, are non-Newtonian, which means they experience shear thinning. A simple explanation of shear thinning is that certain fluids that are thick or viscous under static conditions will thin or become less viscous when shaken, agitated, or otherwise stressed. Inks are highly viscous under normal conditions, but will gradually become less viscous as force or stress is applied. Removing ink from the process eliminates the effects of process shear. This ultimately ensures that you will not get an accurate process reading. And they're easily inaccurate. Efflux cup accuracy depends on consistency of the cup size and consistency of the hole size. The problem is that these are used in an industrial environment. Any ding or dent that causes the cup or hole to vary affects the measurement. Additionally, many of these cups are available very inexpensively from online resources, and they're not always manufactured to the standards required to ensure accuracy. So in summary, pick the right cup. Start by understanding the range of viscosities you will be measuring, then use our online viscosity conversion table and make sure you get the right cup for your fluid. They're inexpensive, quick, easy to use, and they're the benchmark in the industry. You will find that you use it frequently, even if you only use it for spot checking during runs when you're concerned that something may be off. Even then, you must have an experienced and well-trained workforce. Don't rely on the cup for process accuracy. Unless your customer allows you a lot of latitude with your cover, and almost none do anymore, the weaknesses we just discussed introduce too much risk to make the Efflux cup a reliable process viscometer. Even if money is an issue, and it always is, get with a viscosity control expert and let them help you determine your true cost of ineffective process viscosity control. Next, let's turn to the falling piston viscometer. Its strengths are that it is robust. The falling piston viscometer was designed for industrial use. Many have been in continuous use for dozens of years. It's sensitive. The falling piston viscometer detects small changes in viscosity and is excellent for processes requiring very sensitive readings, like printing inks. They're repeatable. The design allows the falling piston viscometer to measure with minimal variation. Not much in a manufacturing environment disturbs either its function or its readings. They're economical. While not nearly as inexpensive as an Efflux cup, The falling piston viscometer is an economical choice compared to other viscometers providing similar or even poorer accuracy. And they consider shear. Many viscometers, like Efflux cups for example, cannot compensate for the non-Newtonian behavior of modern fluids. Because falling piston viscometers use shear in their measurement method, they are perfectly suited to measuring shear thinning fluids. Its weaknesses include moving parts. Although robust, there are still moving parts, and as a result, there are wear items. While not difficult to monitor or to replace, this type of viscometer works best in those environments where preventative or predictive maintenance is a part of the culture. Cleaning. Measuring parts may be exposed to atmosphere, causing ink to dry, and need to be cleaned periodically, especially during color changes. In-tank attachment. Both inline and in-tank versions are available. When operated as an in-tank attachment, often attached to the lid, the falling piston viscometer can be cumbersome to work with, as it has to be lifted in conjunction with the tank lid. It has the potential to become a minor safety issue. And then there's maintenance. The unit routinely needs to be physically removed for visual inspection, cleaning, and part replacement. And then there's installation. The system requires air lines to lift the piston. This can require additional installation time and cost and contribute to additional clutter in the work area. Temperature. The falling piston viscometer does not include a temperature sensor. While not applicable to all processes, it is rapidly becoming the most important variable to control in printing. Further from point of use. Viscosity is most important at the point of use. While controlling viscosity at the tank is good, controlling viscosity at the point of use is better. So, in summary, the falling piston viscometer has an extensive installed base, which shows its effectiveness. It's a very cost-effective solution, especially when compared to other process viscometer options. It has the longest history of any viscometer in the marketplace, and it's one of the most sensitive viscometers available, compatible with both Newtonian and non-Newtonian fluids. Finally, let's address the vibrational viscometer. Its strengths are that it is sensitive. Like the falling piston type, the vibrational viscometer can also detect small changes in viscosity and is well suited for processes requiring very sensitive readings. It's self-cleaning. With no cavities to hold ink, the vibrational viscometer was designed to be easily cleaned. This is important when changing ink colors in a system. Inline. By design, the vibrational viscometer is actually better suited to be used inline than in a tank or on a benchtop. And it's repeatable. The method of measurement allows the vibrational viscometer to measure with minimal variation. If the vibrational frequency is carefully chosen, not much in a manufacturing environment disturbs either its function or its readings. That being said, some models do experience vibrational interference. If the vibrations generated by the press are close to the vibrational frequency of the viscometer, they can interfere with measurement accuracy, repeatability, etc. This varies by manufacturer, mounting provisions, the press on which the viscometer is mounted, and a host of other considerations. Moreover, failure usually means replacement, which can be an expensive proposition. Unlike a falling piston viscometer, a vibrational viscometer cannot be rebuilt. And they don't account for shear. This is also variable by manufacturer. Some versions impart enough energy to create shear in the area surrounding the vibrating rod, but others do not. It is important to know the capability of the sensor in your ink. In summary, the vibrational viscometer has few weaknesses. In recent years, the vibrational viscometer has become popular among printers due to its versatility and ease of use and maintenance. But be aware of the differences. As noted before, some sensors are designed to operate at the wrong frequency and have their readings adversely affected by press vibrations, or they impart insufficient energy to create the shear surrounding the vibrating element necessary to accurately handle non-Newtonian fluids. Why does temperature matter? Remember the honey example? We opened with the honey example to demonstrate the relationship between temperature and viscosity. It's an excellent example because the change is dramatic and everyone is familiar with how honey reacts to temperature. getting thinner as the temperature increases and thicker as the temperature falls. But this is not unique to honey. It's a characteristic of all fluids. It is a physical fluid property, not a defect, and as such, it's both predictable and repeatable. That means we can convert temperature from an uncontrolled variable to a tool we can use to manage viscosity. So given that, how can I control temperature? We've seen a slew of approaches through the years, but the most prevalent and most popular seem to be temperature-controlled rooms, temperature-controlled tanks, temperature compensation, and point-of-use temperature control. So which of these is most effective? Like we did with viscosity measurement methods, let's review the most common methods, discuss their strengths and their weaknesses, and then summarize each. We'll start with temperature-controlled rooms. Their strengths are few, but include the fact that they're relatively simple. Their implementation and control are the same as we all have in our homes. We install a heating and air conditioning system for the room, then place a thermostat on the wall and set it for the temperature we want the ink in the room to be held at. And they provide some improvement, especially when the temperature-controlled room is large enough to include both the ink storage and the printing functions, or the distance between the temperature-controlled room and the press station or stations is very short and the usage rate is very high, so the residence time in the system is very low. And they ensure early consistency. The reason for this is that the ink starts out at the optimal temperature when it's pumped to the press station or stations. This ensures a consistent viscosity-based pressure drop in the system as the ink is pumped along its path. The weaknesses to this approach are many and include the fact that they're expensive. Often, to include storage and printing functions requires a very large room. This is both expensive to build and expensive to heat and cool. If these are being added to an existing operation, it may be necessary to shut down production while construction is in process, which is also an expensive proposition. So they are expensive up front to create and present an ongoing expense to operate. In addition, they miss too many temperature variables. When a liquid is pumped through a dispensing system, friction is generated. The higher the flow rate and pressure, the greater the friction. Furthermore, in addition to the pump, devices along the path like back pressure regulators, orifices, even pipe elbows all contribute to friction. Furthermore, the rolls and plates in the printing process generate a great deal of friction. All of this friction manifests itself as heat in the ink. There is no way for a temperature-controlled room to compensate for these system-generated temperature variables. And they're too far from the point of use. All control is lost when the ink leaves the room. If the temperature-controlled booth is limited to the source functions like storage and pumping, and it's located a distance from the printing operation, the ink will change temperature all along the way to the press. How much it changes will be determined by the rate of consumption, period of downtime, temperature differentials, etc. So, to summarize, temperature-controlled rooms are not entirely without value, but due to their large upfront costs and their ongoing operating costs, they represent an expensive solution. Finally, they're unreliable because too much happens between the source and the point of use that cannot be controlled by the design and function of the room. Next, let's turn our attention to temperature-controlled tanks. Their strengths are that they can be closer to the point of use. Whereas the ink kitchen may be a significant distance from the printing operation, the tank may be located very close to the press. Think of a printing operation where the tank is actually a 5-gallon pail. These are stored remotely in a warehouse, but are brought to the press, more specifically to the actual head where they're being applied for use in the printing process. This means that the distance the fluid travels after it leaves the tank can be much shorter and therefore expose the fluid to less opportunity for temperature change. They can be easy to install and maintain. Jacketed tanks can be installed when the process is created, but tank temperature control can also be added as a retrofit in the form of clamp-on jacketing or temperature-controlled inserts that immerse right in the fluid in the tank. And probably the most attractive feature to this approach is that it's more economical than temperature-controlled rooms. Because they focus temperature control on the fluid instead of the environment, temperature-controlled tanks are more economical to install and operate than temperature-controlled rooms. The weaknesses to this approach are also many, and they include that they miss many temperature variables. Like temperature-controlled rooms, temperature-controlled tanks cannot compensate for process-generated heat. Their point of control is still removed from the process, which will become more obvious later when we discuss point-of-application temperature control. And they can be difficult to maintain if not done correctly. Many forms of tank temperature control involve immersion elements inserted into the fluid through the lid of the tank. These can be difficult to clean and can present issues, especially in applications like printing ink, where the fluid is changed often and cross-contamination is a problem. And so to summarize, temperature-controlled tanks still miss controlling at the point of use. And when used alone, temperature-controlled tanks leave too many variables unmanaged. Like temperature-controlled rooms, once the fluid leaves the tank, the temperature control ends. Without additional hardware, these can still leave temperature variable at the point of application. But that is not to say that these are not without value. In applications like controlling printing ink, temperature-controlled tanks are often combined with point-of-application temperature control systems to create an overall solution. By controlling the tank, evaporation of solvents and amines can be controlled, which can be an important factor in establishing effective process temperature control. Let's continue with temperature compensation. The strengths here are limited, and yet it can provide valuable information. The whole concept of temperature compensation is to determine, based on the viscosity versus temperature curve for a given fluid, what the viscosity would be if the fluid was at a given temperature. This can be very useful when the viscometer is located anywhere but the point of application. But above all else, it supports adding temperature control because it clearly shows why things would be better if the fluid was actually at the temperature and therefore the viscosity predicted. The weaknesses of this approach are many. First, it's based on the flawed logic that it's important to know what the viscosity of the fluid would be at the desired temperature. But in reality, knowing does not equal controlling. The information obtained from the viscometer must be acted upon in order to maintain a consistent and repeatable process. Unfortunately, most people are not sure how to make it useful. This requires knowledge of the specific process and advanced temperature control approaches in order to turn this knowledge into those meaningful actions necessary to bring the process under control. Because temperature compensation is such an abstract concept, it is probably best to just avoid it. This is primarily because, without significant effort to turn it into meaningful action, it offers no real value. As we've noted, it can be used as a tool to generate data that can be used in a process temperature control strategy, but in general, it's far too confusing a method to generate actual results. And that brings us to point-of-use temperature control. Its strengths over other methods are many, starting with the fact that, with this approach, temperature and viscosity are linked. Rather than relying on the addition of solvents or other fluids to the ink, the viscosity is being managed by controlling its temperature. This also provides more accurate viscosity control than other methods. It also provides control where it matters. Because the viscosity is being managed by controlling temperature just as the ink is being applied, this is where accurate viscosity is the most important. And it's cost-effective, because less temperature control equipment is required to control the ink temperature at the point of use. It is often the most cost-effective solution. The weaknesses associated with point-of-use temperature control are related mostly to the logistics involved. In particular, few companies are capable of doing it correctly. This is because designing and implementing a point-of-use temperature control system requires specialized knowledge to assure that the printing process is properly analyzed and the most appropriate system components are selected to do the job in each specific environment. In addition to selecting the right equipment, this type of system requires special attention during installation to assure that there are no gaps in the temperature control envelope that could cause deviations. In summary, point-of-use temperature control represents the future of ink management. As customers' print quality requirements continue to grow more demanding, the fine control this offers will become more important to reducing or eliminating quality holds and customer rejects. Unfortunately, this is too often overlooked because temperature variation has been taken for granted for so long that it's become the status quo. Printers have adopted other ways of addressing the symptoms of temperature variation, like adding solvent or changing analog rolls, and therefore have stopped considering how this is affecting them. But once the effects are brought to your attention, the benefits become obvious after the fact. Implementing accurate ink viscosity control, you can expect improved print quality, fewer quality holds, fewer customer rejects, faster setups, fewer ink adjustments, and fewer pauses for cleaning. We want to thank you for taking the time to view this presentation and hope you found it helpful in your quest to improve your printing process. If you'd like to get more information, please visit our website, www.viscosity.com, where you will find not only a vast array of resources, but also a link to contact one of our viscosity experts for a more personalized approach.